Ladies and gentlemen, students, faculty from mathematics department, and our guest speakers from all across the globe, I welcome you to this 2 days international webinar organized by the Department of Mathematics at Lahore College for Women University, Lahore. My name is Dr. Aqsa Shabir. I'm an associate professor with Electrical Engineering Department. So technically not completely alien to mathematics, though not a true, purebred mathematician. And I also head the Office of Research, Innovation and Commercialization at Lahore College for Women University. So for our international guests, I'll very briefly, comment about our university. We're an all-women university with an enrollment of 17,000 female students at undergraduate as well as graduate level. We have 7 faculties, 46 departments, and including the graduate programs, we have over 100 programs in the university. So as an institution, we are 100 years old, but we're rather, as a university, we're rather in an infancy stage. We've completed 20 years as a university this year. And mathematics is, I believe, one of our oldest departments that we have. I think Dr. Maria will be able to give the exact date when she shares her views. So apart from, of course, our what I very humbly say, our glorious history, mathematics department is it always makes our university very, very proud. They have excellent research portfolio. In fact, probably in the next week, we're holding our annual Research Productivity Awards ceremony, and there we'll be able to, better recognize our wonderful mathematicians who, usually in a department or so, we have 1 or 2 extraordinary researchers, let's say, but I can very proudly, I think, declare that in this particular department, there are several. It's even hard to pick who's the best one amongst them. So they have one of the best, what I may say, cumulative impact and citations from our university, which makes us very, very proud. And they often do several, they take up several initiatives to try to form several international collaborations. They often organize various seminars, various interactions. Even though, we don't typically look at mathematics department as the one that they'll be applying for a lot of funded projects, but even, Dr. Serish herself has often applied for funded projects herself. And, we even have several such initiatives from their end also. So I welcome all our international guest speakers today. It's a wonderful ensemble of guest speakers that we have from what I may say all across the world, because we have Professor Almo from University of Valencia in Spain. We have several speakers from University of Punjab here in Pakistan, as well as University of Central Punjab. Then I think in today's lineup, we also have, an expert from a university based in China. Then tomorrow we have an even wonderful lineup of our guest speakers. There is Professor Goyolchev. Forgive my wrong pronunciation. I'm sure I pronounced it wrongly. From Bulgaria. Then we have Professor Mehmet from Turkey, which I think I'm also very looking forward to listening to his talk, because he's talking about machine learning, which is also my area. Then we again have Professor Mustafa from Xinjiang Normal University, China. Again, speakers from, one speaker from International Research Institute for Climate and Society, USA, and as well as again from University of Punjab. So, before I welcome or ask Dr. Maria, I think before I request Professor Almo, to start, I think I request Dr. Maria to briefly share her views on this webinar, which is an excellent initiative by the mathematics department.
Microphone.
Yeah.
Mute. Thank you, Dr. Aqsa. Thank you very much. First of all, I would like to pay my heartiest gratitude to all the honorable speakers who share their precious time for our students, for their research interest. And I should like to give a brief introduction about mathematics department. Mathematics department, as Dr. Aqsa has told, that it is the oldest department, and the postgraduate education in mathematics department started in 1994. University is now older, about 20 years old, I think so. And the department has today 15 PhD, full-time PhD faculty, and they are doing in diverse research in diverse fields like cosmology and relativity, as you know, factor interpolation techniques, and CAGD, graph theory, signal processing, and fluid dynamics. And these are so many that it is hard to remember at that time. And dynamical system, our latest research. And we have offering bachelor program in mathematics, MS program in mathematics, and the PhD program in mathematics. And overall enrollment in mathematics department is about 400 students. So it is a very, I think, a flourishing department, and students enjoy reading over there. And our faculty is very active, and they want to engage in research, and they are very keen about research collaborations. So if these are the brief introduction about mathematics department. And I am very thankful to Dr. Almo for sparing his morning for us. So Dr. Sarish will let's continue.
No, Maria, allow me another 2 minutes. I missed the most important part, which was, offering some acknowledgements. So it's, before we hand it over to Sarish, I think we need to, offer our appreciation for Dr. Taiba as well as Dr. Sarish for being, the main organizers for this event. And,
Dr. Aksai, factor interpolation technique is the Dr. Taiba.
Looking into the, even the smallest, minutest details. Then, Dr. Maria herself as a chairperson of the department is always wonderful, because it's always with good leadership that, vibrant things happen in a department. And with that, I think it's imperative that on my and my Office of Research, Innovation and Commercialization's behalf and Mathematics Department's behalf that, we offer our gratitude to our Vice Chancellor, Professor Dr. Bushra Mirza, because it is with her encouragement and her leadership that we're always able to, undertake wonderful initiatives. So, Dr. Sarish, let me introduce Professor Almo, and then it will be over to you, with the rest of your speakers. Spain is, in any case, my personal favorite. So I think by that logic, Professor Almo is, I'll be very, honored to introduce Professor Almo.
Yes.
So Professor Almo works at a joint research center of University of Valencia and Spanish Research Council. He carries out his research on the theoretical aspects of gravitational physics. His interests so far have been focused on three main areas: black holes, cosmology, and quantum gravity. In particular, he has studied the properties of quantum fields in curved spaces, with emphasis on the process of black hole evaporation via Hawking radiation and the generation of primordial perturbations during inflation. He's also working on the possibility of explaining the cosmic speedup in terms of dynamical equations different from those of general relativity. Currently, he's also exploring different approaches to quantum gravity from different perspectives, including lessons from solid-state physics. He has carried out his work in collaboration with other researchers in Belgium, Brazil, China, England, Germany, Israel, Italy, Mexico, Portugal, Russia, Spain, Sweden, USA, and now I think by the time of his next talk, it will also have Pakistan included in the list. So, Professor Almo, over to you, and over to you, Dr. Sarish, to continue the rest of the session.
Thank you so much, Dr. Aksa. So before we get started, I have a few announcements for the participants. This is a recurring meeting, so you can rejoin after 40 minutes. And secondly, questions will be taken after the presentations. So if you have any question, you can raise your hand by using option in the Zoom meeting, or you can simply type your question in the chat box. So I will try to take as many questions as I can, but we have time limitations. So thank you so much. And Professor Gonzalo, you can start your presentation now.
Okay, thank you so much for the presentation and the invitation. I cannot share my screen. You need to give me permit for that.
Yes, sir, please. You can share.
Okay. Now. I can do it now. This one. So how much time do I have?
Sir, you have 1 hour. No problem.
Okay, perfect, very good. So thank you so much for the invitation and for being here today. Since this is a varied community, so I wanted to provide an overview on the notion of compact objects and the research that is being done intensely recently on this topic. And also I would like to relate that this presentation to the recent Nobel Prize awarded to Roger Penrose. He got the Nobel Prize in 2020. And precisely because of his mathematical contributions to the theory of black holes. So I think this is a very appropriate place to talk about this. So, so everything starts with Einstein's theory of gravity. Okay, so general relativity changed our view of gravitation and actually provided a complete new approach to the understanding of cosmology and gravitational systems. And one of the things that we quickly realized is that the general relativity can describe stellar objects with properties that are slightly different from those of general relativity. But as the research progressed in this field, we realized, and not only the theoretical research or mathematical research, also new observational discoveries about compact objects like white dwarfs, very compact stars. This observation suggested that extreme forms of matter, of condensed matter, could exist in nature. Okay, so the first solutions, like the Schwarzschild solution that were found in general relativity, began to be explored in more detail, okay, in such a way that new objects that initially were considered as exotic solutions began to be considered as something physically possible, okay, and this is in particular the case of black holes. So the idea of giving complete meaning to the Schwarzschild solution in all regions of space-time was a previous idea in the 60s. And at that time, this gentleman here, Roger Penrose, he made outstanding original contributions to the field of mathematics and in gravitation that were worth a Nobel Prize in 2020. So his results, his analysis of black holes, and not only black holes, the notion of trapped surface in gravitation, and the implications that this had for physical systems was really unique. So his contributions are considered as the main contribution in gravitational physics beyond Einstein's theory. So Einstein made the biggest contribution, and then the next milestone corresponds to Roger Penrose. This is why he won the Nobel Prize. Okay, so and it is crucial to understand the implications of his work, because it implies that general relativity under reasonable conditions may lead to the formation of singularities. And this is an impressive result, but from the physical perspective, it implies that the theory has limitations. Okay, so this important result indicates that the theory must be improved, or some things must be modified. Okay, and this is the key point of this talk, because singularities can exist in general relativity, but singularities cannot exist in nature. So something must be different. So the Schwarzschild solution cannot be an exact solution of nature. It is a solution, an exact solution of Einstein's equations, but cannot be exactly realized in nature. Unlike the Schwarzschild solution, any other black hole solution known in general relativity, because they imply the existence of singularities. So alternative objects must exist in nature. Okay, so, and they can be very similar to the predictions of general relativity, but cannot be exactly the same. Okay, and this is what motivates the last point. How we find those exotic new objects and how do we characterize them. So all this starts with Einstein's theory. Okay, so Einstein proposed his theory in 1915, and once you propose a new theory of gravity, so it is natural to check its predictions. Okay, and one of the key predictions that Einstein explored was the perihelion shift of Mercury. Okay, this was a well-known phenomenon. So the fact that the perihelion of Mercury was precessing was well known from the 19th, already in the 19th century, and there was no explanation at that time. So a new theory of gravity was a nice opportunity to check if that effect could be justified. Okay, so general relativity succeeded in that. Okay, and the deflection of light was another prediction that was somehow expected, no? Already from the special theory of relativity, because energy and mass are related by this famous equation. And since mass feels the effects of gravity, so it was somehow expected that light could be deflected by gravitational fields, like the field of the sun. But the existence of black holes, this is something that was completely unexpected. So, and this is probably the most fascinating prediction of general relativity. The possibility of having matter compressed at huge densities, such that the space-time structure, the causal structure of space-time is so much modified, is something that nobody could have guessed or expected at the beginning when the theory was proposed. And in fact, it took many years to really understand that this was really possible. So the next important contribution came just 1 year later by Karl Schwarzschild, and he proposed, he found actually an exact solution of Einstein's equations, imposing spherical symmetry. You know, this is the spherical sector, and the Einstein's equations in vacuum admit an exact solution of this form. And this is very simple. This is extremely simple, because when alpha is 0, we just recover the Minkowski line element in spherical coordinates. Okay. So this is very simple line element, but the implications are huge. In particular, if we want to have agreement with Newtonian gravity, we need to identify the constant alpha with 2 times the mass of the object. Like in this case, we will think about the sun. And this magnitude, alpha over r, at the surface of the sun is really small. It never gets bigger than 10 to minus 6. So it's one part in a million. So this line element is basically like the line element of Minkowski. Not really Minkowski.
21,200 तुम्हारा था.
Okay, I didn't know that my microphone was off. Can you hear me now?
It was interruption, so I have to mute everyone. So you can.
Yeah. Yes, I understand. But can you hear me now?
Yes, sir.
Yeah. Okay. Thank you. Thank you so much.
Exactly.
So this line element is very close to Minkowski, because this quantity is very small. But even so, it is enough to keep all the planets around the sun. So it's really impressive that this simple line element with these tiny corrections can do so much for us. Okay, so but at the time this line element, at the time this solution was proposed, there was no reason to believe that that this line element could be a solution valid over all the whole space-time. Okay, it was supposed to be just valid for the exterior of a star, no, in the empty region. For the interior, we should find different solutions. And this is because we didn't have any for extremely in particular for white dwarfs, for instance, were not well known at that time when the Schwarzschild solution was proposed. The existence of white dwarfs was still not on very solid grounds. I think that by this time, probably only 2 or 3 white dwarfs were suspected to exist, but very little was known about them. So we didn't have any evidence about very compact stars. And by very compact stars, I mean objects for which this quantity could be of order 10 to minus 1 or 10 to minus 2. We didn't have any evidence for that. Okay, so this solution could only be interesting outside of massive objects. But even so, Schwarzschild found interior solutions, okay, with fluids. He considered the equations of general relativity with perfect fluids. And in particular, he obtained exact solutions for constant density stars. Okay, these solutions are well known in the literature. You can find them in textbooks like Wald's book on general relativity and many others. And when you compute the pressure associated to those constant density stars, then you find that the pressure at the center of the object is given by this formula. Okay, this expression relates the central pressure at the center of the star with the constant density of the star. And what one finds is that the denominator, this quantity here, can become 0, okay, at some point. And if this is 0, then obviously the pressure becomes infinite. So what this is indicating is that we cannot put any amount of mass inside a given radius, okay? In fact, the maximum mass that can be put inside a star of constant density and of given radius R0 is this quantity. When this 9/4 R0 is called the Bugdal's limit. Okay, so this means that already the simplest solutions with matter were indicating that something that we cannot have arbitrarily massive stars or arbitrarily compact objects. Okay, there were some limits. And if one improves the description of stars, it follows that this Bugdal's limit applies to any stellar configuration with a smooth density profile, so that the maximum density is at the center and then it decays smoothly towards the outside. So it seems that stars cannot have arbitrary masses. Okay, so this was a very deep and interesting result. And well, things evolved quite quickly at that time, because in the 1930s, Chandrasekhar, who actually I think was born in Lahore, this probably, if I'm not wrong, Chandrasekhar made an impressive discovery. He found that contrary to expectations at that time, all the stars that burn their nuclear material cannot have arbitrary masses, because when the nuclear reactions stop, the core of the star collapses and is sustained only by electron degeneracy pressure. But if you combine this idea or this kind of pressure, these properties of quantum gases, quantum fluids, with equations of general relativity, what you find is that electron degeneracy pressure cannot support stars with more mass than this limit that was found by Chandrasekhar, 1.4 masses, solar masses. So this was in conflict with the established theory at that time for stellar evolution, and the result was not accepted very rapidly. But more research was done, and already before the end of that decade, in 1939, Oppenheimer and Volkov found that similar bounds existed for neutron stars.
Dr. Gonzalo, sorry for the interruption. We have 2 minutes for this meeting, so we have to rejoin after 2 minutes.
To rejoin again?
After 2 minutes, yes.
Using the same link, right?
Yes, using the same link.
Okay, very good.
Thank you. Thank you.
I will continue and then rejoin. Thanks. Okay, so even for neutron stars, so there was a maximum mass for this object that could not surpass this limit of 2-3 masses. So the question was natural. What happens if we have more massive objects, or if a neutron star is accreting mass, like white dwarfs? White dwarfs can accrete mass, and then they grow bigger and surpass these limits. So what happens when they surpass these limits? So this was a natural question. And so this was found in the 1939, and already that year, Oppenheimer and Snyder considered the first model of gravitational collapse. So this model was so successful and is so clear and so robust that even today, our understanding of gravitational collapse is well described by their model. Okay, so so the model consists of an interior represented by a Freeman-Rosen-Walker cosmology, and an exterior represented by the Schwarzschild solution. So I will continue in a few seconds once this is stopped.
Okay, thank you, Professor Gonzalo. We will continue after few seconds. Yeah.
Thank you.
So, dear participants, please rejoin after few seconds.
Mm-hmm. Oh. I need to share my screen again. Please. I'm not allowed to share the screen. Please, Dr. Serish, can you let me share the screen?
Yes, sir. Please, you can share your screen now.
Now I can. Yes, thank you so much. So as I was saying, the Oppenheimer and Snyder model represented a simplified model of gravitational collapse, assuming that there are no energy mechanisms to produce pressure to counterbalance gravitational collapse, because hydrostatic equilibrium is lost. And then the simplest model consists of a fluid of a given density without pressure that has homogeneous density in a certain region and is vacuum outside. So this sphere of gas, when allowed to evolve, it collapses, and the collapse proceeds in a finite time. Okay, any observer falling with the fluid will see the energy density to grow up to infinity and reach zero volume in finite proper time, while an external observer will see the star freezing as it approaches the Schwarzschild radius, the event horizon. So this is the prototypical model of gravitational collapse. It indicates that infinite densities can occur, that geodesics can be stopped, cannot be extended beyond a certain point, and obviously this kind of end stage for a massive star was a bit confusing. It was a problem, it was a challenge for physics, because it was suggesting that infinite densities could be achieved inside a collapsed object. So a lot of research was motivated by this. just to check how robust the Oppenheimer-Snyder conclusions were, because it implied lots of simplifications, because it's assuming a pressureless fluid, it's assuming that there is perfect sphericity, that the object is non-rotating. And obviously, any of these modifications, relaxing any of these conditions, could change the conclusions, okay? So some researchers explored Bianchi models, which are anisotropic models, so breaking sphericity, and that didn't change anything. Raichaudhuri and Komar consider the evolution of geodesic congruences to study the fate of geodesics, introducing some mathematical techniques that were crucial for Roger Penrose theorems. Okay, so the contributions of Raichaudhuri were fundamental for the development of the singularity theorems. And then Komar also made important additions to the original approach of Raichaudhuri, considering the energy conditions, and they both found general results describing the focusing of geodesics, how geodesic congruences evolve under given initial conditions. So these are primitive versions of the singularity theorems that were valid in certain restricted conditions, okay? At the same time, at that time, Lifshitz and Kalatnikov also explored these problems, but they concluded that the effects observed were just caustics, that they were not really physical singularities, okay? But further research in 1965 by Doroskevich, Seldovic, and Novikov, they found that with improved models as compared to Oppenheimer-Snyder, non-spherical models with different kinds of perturbations, they found that even with away from sphericity and with pressures and energy generation mechanisms, the final stages of the collapse were essentially the same as those already observed by Oppenheimer and Snyder. So their conclusions were preserved, were very robust, okay? And while all this was taking place, John Wheeler asked Roger Penrose to study the problem of singularities. And he wrote a 2-page paper in Physical Review Letters that was worth a Nobel Prize, okay? And this is the revolutionary contribution of Roger Penrose to this important problem already raised by Oppenheimer and Snyder with their model in the 30s. So Penrose showed that neither breaking symmetries nor other considerations about the properties of matter can avoid the formation of a singularity once certain conditions are satisfied, okay? So the singularity was identified via the existence of incomplete geodesics. So basically they were following the approach initiated by Raichaudhuri and Komar. And to prove this result under very general conditions, even though they are not the most general, okay, he had to introduce the notion of trapped surface. Okay, a trapped surface was a new mathematical concept, okay, that was further developed after these works by Penrose. This was a new concept in physics and mathematics. And this trapped surface is defined in terms of inequalities, and this gives robustness to the conclusions, okay, because they are not demanding certain specific conditions, but they impose some inequalities, and this relaxes, this gives more freedom. If something happens, for instance, for a spherically symmetric system, the fact of expressing those results in terms of inequalities means that for a slightly not spherical system, it will also be valid, okay, for instance. So all the details about the theorems can be found in this paper and others, but this is a nice review by Senovilla and Garfinkel, which I strongly recommend. So the theorem, Penrose theorem, basically says that if the luminous convergence condition is satisfied, then there exists a non-compact Cauchy hypersurface, and if there exists a non-compact Cauchy hypersurface, and there exists a future-directed trap surface, so we need these three conditions, then incomplete light geodesics will occur in the future. Okay, so if all these three conditions about the initial conditions of matter and the existence of a trap surface occur simultaneously, then we have a singularity. So this was a very important result, because it means that under very general conditions, general relativity predicts the existence of incomplete geodesics, and incomplete geodesics mean that we can, for instance, information is propagated via null geodesics, light rays. Okay, so if light ray trajectories are not do not last forever, then and they stop at a given finite time, this means that information can be destroyed, classical or quantum. But this is something really deep. If you can destroy information, you have a terrible problem for the initial value formulation of your theories, okay? Because your initial data can be destroyed. Also, so you lose predictability. Also, if singularities can be observed, then new information can come out from the singularities, and therefore predictability again is in danger, because your initial data will not be enough to predict the future evolution of the system, because the singularity can be producing new data. On the other hand, if we have incomplete time-like geodesics, this means that observers can be destroyed or can be created. So, and this is really a deep limitation for doing physics, because physics is essentially the process of measuring and exchanging information. So if the measurement, if the measuring device is destroyed, so there is no possibility of doing physics. Okay, so this is really the existence of these singularities, which is manifest by the incompleteness of geodesics, is a deep and terrible physical situation. Okay, this is a terrible situation for a physical theory, and therefore this means something. Okay, we have to do something to improve the description of compact objects. Oops, something happened to my presentation. So just let me. Now it's me, it's not you. Okay, I'm back. Okay, can you see that? Okay, excellent. So this means that we need to go beyond the limits defined by these theorems. And this means that either we need a new theory of gravity, or we need to break some of the conditions on the matter fields, just to avoid the consequences, the implications of this theorem. So since trap surface were a key contribution of Penrose analysis, so a simple explanation is provided by this analogy. So this is an analogy in which the space-time is represented by the fluid, the river, okay, and the matter and electromagnetic fields information is represented by this fish, okay? So when we are in this region outside, we are here outside, this line here is the horizon, and down here we have the singularity. Okay, so in the outside region, fish can go in both directions, can go upstream or downstream. Okay, they can move freely in both directions. But as they approach the horizon, so it is more difficult for them to move in the upstream direction. Okay, so and once they cross, so if they cross this line, then even if they swim trying to get out of that region, they swim upstream, they will be falling with the flow of the water, so they cannot escape. So that is essentially what a trap surface means, that all signals going in either direction, up or down, they are all going to fall. Okay, they cannot escape. This is what represents a trap surface. Okay, and here is represented in terms of this simple analogy. Okay, so what happened in the Oppenheimer and Snyder model is also represented in these diagrams. The Penrose diagrams, this is a Penrose diagram, and according to the Nobel Academy, the Swedish Academy of Sciences, the Penrose diagrams are a fundamental tool for understanding gravitational physics, and so I think it's worth representing them here in this talk. So in this other illustration that is represented as a space-time diagram, so the original collapsing matter is represented by this circle here, and as it has a radius, an original radius, and as time goes by, the radius is decreasing. Okay, R goes to 0 as time evolves. Right? This is time, and eventually the object collapses to 0 radius. So during this time, up to here, we don't have trap surfaces. Okay, but once we cross this line, beyond this instant, an apparent horizon begins to grow, and then the causal structure changes in such a way that light cones locally always point toward the singularity. So any light ray emitted in this region will end up in the singularity. There is no possibility of them escaping from this trap region. Okay, this is what represents this space-time diagram, and the region of trapped surfaces is described here. These are the trapped surfaces. So no light ray can escape from this region. They all fall either in that direction or in this direction and will eventually hit the singularity. Okay, very good. So I already explained this, why geodesic completeness. So because this is crucial for the predictability of the theory, and from the existence of singularities. So motivated by that, Penrose suggested that the universe should be somehow protected by these singularities. The implications that they have for predictability should be somehow cured by some protective measure, like and he proposed this cosmic censorship conjecture. So he said that if singularities exist, then they should have no observable effects in the sense that given initial data, the subsequent evolution should be uniquely determined by those initial data. So singularities should not have an impact on them. So if singularities can interact with the initial data, then predictability is lost. Okay, because new information is added that was not on the original data surface. Okay, so this is why it is assumed that if singularities exist, they should be hidden behind an event horizon. So this somehow is suggesting that event horizons are there to avoid observing space-time singularities. But this is a very simplistic view, because from a physical perspective, the event horizon arises at a scale of order the mass of the object, while the singularity arises at a scale completely different. It's when R goes to 0. So there is no reason why the two scales should be related. There is no reason why what happens at R equal to 0 should be conditioning the existence of something at much larger scales. Okay, and motivated by this, the first non-singular black hole model was proposed by Bardeen in 1968. Okay, so now we are going to begin the exploration of alternative objects that are not exactly the black holes of general relativity. Okay, since general relativity is predicting that black holes are going to have singularities, and this is terrible for physics. So we are now going to explore alternative solutions that avoid those difficulties. Okay, and bypass somehow the implications of the singularity theorems. So Bardeen proposed this space-time assuming spherical symmetry at a typical ansatz for the time and radius sector, and he just changed the function by this. Okay, and as you can see, if this g, this constant, goes to 0, then we recover Schwarzschild. Okay, but when g is not 0, the limit r going to 0 is modified. Okay, and it's modified in such a way that the space-time becomes non-singular. Okay, so this is a nice example of an object that can have similar physics as the Schwarzschild black hole for larger radii, but has completely regular behavior near r equal to 0 at the center. Okay, so this is possible within general relativity because this particular solution can be generated by a nonlinear magnetic monopole. Okay, and that kind of matter violates the strong energy condition. Okay, the energy conditions are crucial in the singularity theorem. So if you manage to violate one of those conditions, you can escape the consequences of the theorems. And this model was the first one. Note that this was from the 1968 and the theorem is from 65. So only 3 years later, this alternative solution was proposed as a toy model. Okay, there was no proof. Simply the line element was designed. So he didn't even know that this was due to a magnetic monopole. This was clarified in the early 2000s. Okay. So the important thing is that the center of the object now behaves like the de Sitter core, like a region of constant density, right? Or like described by a de Sitter solution with constant curvature, a maximally homogeneous and isotropic, maximally symmetric solution. And thus, it was really a very interesting model that motivated many different other alternative proposals. The Penrose diagram for this space-time is like this. Okay, the relevant region is here. We live here. We live here. Okay, and then this is the external horizon. This is very similar to the Reisner-Nordstrom black hole. Reisner-Nordstrom black hole, similar. Okay, it's similar because it has 2 event horizons, the exterior and the interior horizon. Interior is also a Cauchy horizon, but in Reisner-Nordstrom, r equal to 0 represents a singularity. Okay, it has here a singularity, but now the model doesn't have that ill behavior. Okay, it is well behaved at the center, so any incoming light ray can get to the center and reflect and continue their trip to other universes. Okay, so this solution was really doing something very, very nice. That was a static solution, and improved models were proposed later, also motivated by similar arguments. And this is particularly interesting, Haywards' model proposed in 2006, where he considered deformation. Here, this is the mass profile, the formation and evaporation of a black hole, okay, of a regular black hole. So he considered the formation of a black hole with some incoming energy flux, and that represents the growth of the mass here, a region in which the object stays stationary, okay, and then here evaporation proceeds, evaporation via Hawking radiation, okay, Hawking radiation. So in this process, the global evolution of space-time produces trapped surfaces in this region, okay? So just to remember you, the trapped region in the Bardeen case is all this square. Okay, this square represents the trapped regions. Now in the Bardeen solution, the trapped regions are only restricted to this area here, which is finite, and therefore there is no global event horizon. Okay, so the space-time initially begins as flat and forms a black hole, stays as a black hole, and then evaporates to produce another flat asymptotic region. So this is a very nice model. It satisfies Einstein's equations as a kind of Baedia type solution, where the mass function is this variable function mv. Okay, so it was a very nice and interesting model, and all of these at some point had an apparent horizon or an outer and inner horizons for some time. They had trapped surfaces, okay, and avoid singularities for some time, at late times at least. And the center is like the Sitter core, okay? So Bardeen's model and Haywards model have the peculiarity that they avoid the singularity via a de Sitter core, okay? Near when R goes to 0, R going to 0, the center is dominated by a de Sitter-like solution, a de Sitter core, okay? But more recently, we found, and this is now a contribution in which I participated, we found alternative non-singular objects that are not, do not have an internal de Sitter core, okay? Instead, they look more like wormholes. So the radial function, this R squared, which represents the spherical sector, the area of the spherical sector, has this kind of behavior, okay? The dashed line represents GR, the typical GR solution, and this solid line is the modified theory of gravity. Modified gravity. And what happens here is that the two spheres, so the collapsing, for example, a flash of light that collapses is going to reduce the area of the two surfaces of the spherical surface, but it does not collapse to a point. Simply, it reaches a minimum surface and then bounces. Okay, so this is like a wormhole, that there is a wormhole inside of the black hole. So there is an event horizon, but instead of reaching R equal to 0, like in the standard black holes of general relativity, or finding a de Sitter core, like in these modified models, this solution, this is an exact solution, combining this gravity theory with an electric field. Okay, then when you solve the equations, you find these solutions, and you find that this wormhole arises inside of the black hole. Obviously, this is nice. It has very interesting physical features, but the particular form of this function G is ugly. Okay, it's not really very nice because it's written in terms of hypergeometric functions. It's an exact solution, but exact solutions are not always beautiful. Okay, but it is interesting for many reasons. Because it avoids it allows for geodesic completeness. Okay, at the wormhole throat, geodesics can be extended to the other region, and in this way we avoid the singularities of general relativity. And one of the most interesting things of that result is that it captures the essence of more recent models. Okay. That are produced considering more advanced quantization techniques. Okay, the original model, this model is just a proposal inspired by semi-classical approaches to quantum gravity, but there are other approaches like loop quantum gravity that find similar behaviors. Okay, in particular, if you look at the radial sector of this solution that comes from the loop quantum gravity techniques. So the structure is basically that the area function is similar to that to the one that we found. Okay, it is doing qualitatively the same thing. Okay, the coordinate x can go from plus infinity to minus infinity. So you have a minimum when x is 0 that takes the value x0, and also the time and our components are finite. So everything is very similar to what we found, simply that in simpler mathematical terms and obtained via completely different approach motivated by quantum gravity. Okay, the Penrose diagram has this structure and is basically the same that we found. Even more recently, also in the last few years, simplified models of black holes with internal wormhole. This is what they call black bounces. Okay, black bounces. This is the term used by Wiese and Simpson. They proposed a set of heuristic models. Okay, this is just an example. They have different other line elements in which the same idea of an internal wormhole is proposed to get rid of the singularity. So as you can see, there are alternative ways to get rid of the singularity, either via a de Sitter core or in terms of an internal wormhole. And there are also other ways to consider compact objects that are non-singular within general relativity and beyond. And an example are boson stars. I like boson stars because you have to solve the equations of general relativity with a specific distribution of matter. You consider like a scalar field and then consider the whole set of equations, and you numerically solve the problem because analytically there is no way to do it. Okay, you have to do it numerically, and then numerically you can find static solutions. So you can show that those boson stars exist and they can have reasonable radii and mass, and then you can do perturbations and study evolution, time evolution. So you can perturb and check if the solutions are stable, if they are not stable, if they are stable or not under density perturbations, or if you put them to rotate. When you have rotating solutions of this kind, you can check their stability. And all those numerical experiments are very interesting to see if extremely compact objects similar to black holes but different in nature could exist. And of course, these boson stars are a very nice candidate that are being explored, and we already know a lot about them, and are a reasonable candidate for alternative compact objects. So these objects have been explored in general relativity, but also we are looking at them in FFR theories. Okay, so just these plots represent some existence, the existent region where there exist solutions, and the blue curve represents the solution of GR, and the other curves some modifications with a non-zero parameter here. Okay, as you can see, for positive values of the parameter, the solutions are very similar to what one finds in general relativity. If we change the sign when this parameter is negative, then the family of solutions is slightly different. We don't have anymore the spiral behavior, it's something different. So, but in any case, these new objects exist, okay? And these solutions are very nice and can be explored under under many different conditions, like considering self-interactions. And if you consider self-interactions, what you see is that the numerical solutions are almost identical to those of general relativity. So if these objects exist, it will be very difficult to see if they are solutions of GR or of other theories of gravity, okay? Because self-interactions induce a huge degeneracy in the solutions. Okay, so the good thing of boson stars is that it would be nice, it would be very nice to see if under perturbations, these stars could collapse and form non-singular objects. Okay, so it would be very nice to see if the de Sitter curves can be generated dynamically, or even if wormholes can be generated dynamically. Okay, this is the really relevant aspect of these boson stars and other exotic objects. If they can produce the kind of non-singular objects that we observe from different approaches to quantum gravity. Okay, this is our main motivation. And well, now that we have different proposals, alternatives to black holes, we need to see if we can find them. How do we find them? How can we compare these objects with the black holes predicted by general relativity? So the only way to do it is by exploring the universe, doing physics. So we can study gravitational waves, okay, and in particular quasi-normal modes. We can also explore the optical properties of compact objects illuminated by accretion disks, okay? And we can also explore the interaction of these objects with matter waves. But from an experimental or astrophysical perspective, this part is more difficult to achieve. So these two are really are becoming accessible to observations and to experiments nowadays. In particular, for an example is for quasi-normal modes. I'm presenting here an illustration, okay? If you consider the Schwarzschild solution, this is the Schwarzschild solution for a given theory of gravity. In this particular case, I'm considering general relativity modified by a Chern-Simons term. Then you can explore the perturbations of these solutions, okay, starting with this background. So you start the perturbations of this background. And depending on the theory of gravity that you have, the equations that describe the perturbations are going to be different. Okay, and this is the key thing, because these perturbations represent gravitational waves and tell us how these objects, these compact objects, vibrate. So even if we have the object looks like the Schwarzschild solution of general relativity, the way they oscillate and produce gravitational waves when perturbed can be completely different from the prediction of general relativity. And this is where gravitational waves are so important, okay? So in this particular theory, modified gravity theory, the Chern-Simons model, so we find that there is a scalar field coupled to gravity. And the perturbations of the scalar field satisfy these horrible equations. They are really horrible in this form. And when you try to solve them, you suffer a lot, okay? It takes time, and you need to spend a lot of time to put them in the right form, to analyze them in the standard approach, and then obtain solutions. But it can be done, okay? And then, so you have the perturbations of the scalar field, you have the perturbations of the metric, modify the equations for the scalar field, modify the equations for the scalar perturbations, and then those equations can be written in this form, which is a wave-like equation, okay, that couples the tensorial modes with the scalar. This is the scalar, this is the tensor. And here we have the scalar, the scalar coupled to the tensor. So we have scalar modes and tensor modes that are coupled, okay? So the way they are coupled, the particular form of these potentials changes from theory to theory, okay? And so the resulting gravitational waves are going to be different. So exploring those waves with detectors, we could find signatures not only of the existence of those waves, but of the dynamics of the particular theory that is producing those waves or governing those waves, okay? And as an example, you can see here in these plots what quasi-normal modes do. Quasi-normal modes, these oscillations, they are quasi-stable, quasi-stationary frequencies modes that have an evolving amplitude. You can see that the amplitude is changing here with time. The amplitude is decaying and oscillates with given frequencies. Okay, so we can explore those frequencies, the decay rate, and if we are able to measure this region and wait long enough to see farther away, we will see that the oscillations stop at some time. Okay, so this is the oscillation region, oscillation modes, and this is the power law decay. So there is a change of regime in this, in the evolution of quasi-normal modes, and this power law region is described by a power law of this form, okay, with t raised to some power. And this power in general relativity is typically, can be analytically shown with observations.
Dr. Gonzalo, we have to rejoin.
We have,
rejoin, we have to rejoin.
Okay, okay, perfect. I will rejoin in a second. Okay, very good. So, as I said, in general relativity, this is the power, okay? But in other theories, this can change, like in the Chern-Simons theory. You see that the prediction is different. So observing this could allow to contrast and to rule out some theories and others. Okay, we'll be back in less than a minute.
Okay, thank you, sir. So we'll be coming back again.
Sure. Wave. Yes. So besides the gravitational wave signatures of compact objects that can be used to confront between general relativity and other theories, we can also explore the electromagnetic radiation that they emit. In particular, it is now becoming accessible, the direct observation of black holes, not really black holes, of very compact objects at the center of galaxies, like this. This is the central object at the center of the Milky Way. This is Sagittarius A star. That this observation, this picture is compatible with the predictions of general relativity for rotating black holes. Okay, it is compatible, but we don't have a complete certainty that it is really a black hole. We just know that it is a very compact object with luminous properties that are similar to those expected for black holes. But this picture represents mainly the contribution of the direct image and the lensing effects. But there is a lot more in this in the electromagnetic emission of compact objects that still needs to be explored before we can conclude with 100% confidence that this is really produced by a black hole. Okay, what we can say is that there is an extremely compact object at the center with an accretion disk. Okay, and this is the light or the electromagnetic radiation that comes from radio waves that we observe from this accretion disk. Okay, so the way we produce these images is basically by considering a systematic ray tracing of geodesics. It's nothing more complex than that, and also not too simple. So by reproducing all those geodesics, we can put different. The geodesics are determined by the background geometry. Okay, geodesics are something, are a property of the background. The intensity profile, the luminosity profile, is something that depends also on the characteristics of the accretion disk. Okay, so we have two effects. On the one hand, we have the geometry that generates the geodesics on which the accretion disk is moving and the geodesics are propagating, but also we need the particular details, the composition and the structure of the accretion disk. So extracting information from these images is extremely challenging because we need to have a complete or a very good control of the astrophysics of the accretion disk, and then have a good understanding of the background geometry. So, and this is not trivial. It is not easy to disentangle the two effects from the images. Okay, and this is the real challenge. So to do it, we need to learn. And I'm going here to show a few examples of how these images like this are produced, okay, with spherically symmetric objects, and we'll simply illustrate the differences that we can find between something like a black hole. This is a black hole, this is another black hole, but this is a wormhole, okay? So we are representing here that the accretion disk is here, okay? And we are observers on this side, okay? We are looking from here. This is the eye, okay? So basically we have to draw all the geodesics, and as you can see, geodesics can have a weak deflection like this, the ones that we see here. They are weakly deflected, they are going in that direction, okay? And these geodesics that are represented in green cut the accretion disk only once, okay? Because as much they can come from here, and you see the deflection, okay? And they go away to plus infinity, okay? To plus infinity. Okay, so this cuts only once. These orange ones, as you can see, they come here, they cut the disk, but they get deflected and they can cut again here. So twice, 2 times, 1 and 2. So this second, what this really means is that a light ray emitted from the backside of the accretion disk can travel in this direction, okay, get strongly deflected by the gravitational action and the gravitational field, cross again the accretion disk, and then travel towards the detector. Detected. Okay, so this light ray is picking up intensity from here and from here. Okay, and there are other light rays that can cut the disk more than once, like these ones. These that come from 5, they can travel, they cut here once, twice, and they can even cut 3 times. Okay, so as you can see, there are different regions, geodesics coming from different regions can pick up intensity from different regions of the accretion disk. So, and this will produce different images in the detector. Okay, so these images are going to be crucial for the reconstruction of the final picture. Okay, so we don't see many differences between these 3 plots. You have to analyze them in detail. Okay, but I will show you how these things change. Okay, so for instance, if you consider that the accretion disk is represented by this intensity profile, this is the intensity, of light, and the accretion disk is defined from r equal to 6m to infinity. Okay, r equal to 6m represents the innermost stable circular orbit. Okay, so this is an accretion disk that stays around the black hole, okay, with maximum luminosity at r equal to 6, and then that luminosity decays with distance. Okay, so the light coming from this accretion disk in the previous plot, this accretion disk basically would start here. It only reaches up to here. So there is nothing in this region. Okay, only here. Okay, so the light coming from here can produce this external ring, this side. Okay, this is the external ring, and it's represented by this intensity peak. This is the direct image. The direct image. Okay, this is like if you see, for instance, the planet Saturn from the North Pole, you see the rings. Okay, so you see the direct image of the rings. Okay, Now, Saturn doesn't have a strong gravity, so we can only see the direct image. A black hole has such a strong gravity that the backside of the rings can get deflected and reach us. Okay, so that is a lensed effect, and this is the lens. This ring here is the lensed ring, and it's represented by this lens. So it is showing us the light rays that cut twice, like this. This one that cuts one and then twice. Okay, this is the lensed image. Okay, and then there is this little peak here that is not observable in this. Well, actually, I think you can see it like this. You see some little ring here, over there. That simply represents the light rays that are in the photon sphere, those that can cut the axis more than twice, 3 times, or even spend many times around the black hole. Okay, so just zooming in. Yeah,
Professor Gonzalo, sorry for the interruption. We have to finish this in 5 to 7 minutes.
Perfect, no problem. I'm just almost done. I'm just finishing. I was giving details just to.
Yeah. Thank you, sir. Thank you.
Okay, so as I was saying, this little intensity peak here is barely observable, but is really here. Okay, it's very thin, and this is something that must be there. So this is a clean view of reality. Reality is just like this. Obviously, here we can only see the direct image and the lensed image, okay, which are these 2 big rings. But the little rings inside are not observable here because we don't have enough precision yet. Okay, so in the future we will be able to observe those rings, and then we will be able to discriminate between different objects. Okay, for instance, there are objects that have more rings than general relativity. General relativity only have the direct, the lensed, and the light ring, but there are other objects like this one that can have many other rings. As you can see, all these internal rings are not present in general relativity, but appear in other theories of gravity. Okay, and depending on the properties of the accretion disk, they can look like this, or look like this, or like this. These 3 pictures represent the same background geometry. We are only changing the properties of the accretion disk, the astrophysics. Okay, so it is really challenging. It's going to be very difficult to extract information about the background geometry by looking at these images, but we have to do it to progress. Okay, so to summarize, we have seen, I have tried to motivate that singularities are predicted by general relativity, but they cannot be physical because they have terrible implications for our understanding of physics and the evolution of times, predictability, of systems, predictability. And therefore, this requires modifications either of the matter sector, that could be boson stars or other very compact objects like quark stars or other forms of matter, or maybe modifications of the dynamics due to quantum gravity or to new classical symmetries or whatever. So, but we need something different. You cannot stick absolutely to general relativity. We need to go away from that. And then gravitational waves and electromagnetic radiation can help us better understand the kinds of compact objects that there are in nature, and if they look like black holes, if they have event horizons, if they have wormhole structure, if they have singularities, if they don't have singularities. So this is something that is going to be very exciting in the coming years and for many years, but we still need to improve a lot our detectors of gravitational waves and of electromagnetic radiation. And well, that's all I want to say. Thank you so much.
Okay, thank you so much, Professor Gonzalo, for such a nice presentation, and it was indeed an amazing explanation of singularity-free black holes. So it's time for questions. So, okay, I think Muntazim was asking some question.
Assalamu alaikum. How are you, Professor?
I'm fine, thank you.
It was a nice presentation, and it was amazed to see you here. I have learned about a few of your works. I have started. Basically, my field is on random number generation, modeling, and simulation, and I'm working on new methods of random number generation. Use of these methods on cryptography and network security. It was amazing for me to learn about the boson star today. It was good. I request you that I need a lot of help maybe from your side to generate new methods of random number generations based on the model of boson stars. So will you please help me in this direction?
Can you repeat the question more precisely?
I need your help to please guide me in that direction. Can we generate a new model of random number generation using the boson star?
Okay, so just for that, if you want to discuss, just send me an email and we can talk to see if we can find some review article or something that can help you.
Okay, thank you. Thank you.
Sadia Karim was asking some question. Okay, Shabnam Ashraf. Shabnam Ashraf is also asking some questions. Shabnam Ashraf.
Assalamu alaikum, sir. How are you?
I'm fine, thank you.
So you said that singularity is identified the existence of incomplete geodesic. I ask which identity existence of complete geodesic?
If geodesics are complete, then you don't have any problem with information loss or the process of making measurements. So the problems arises when information disappears or information is created, or when the observers are destroyed or created. This is the problem with geodesics.
Okay, and sir, how singularity are unphysical? Kindly explain.
Yes, physics, nature is about finite quantities, essentially.
Okay.
And so,
sir,
if a singularity tells you, if some region, some theory tells you that some quantity, like density, is infinite, it's because the theory is not working well.
Okay, and sir, in which Schwarzschild geodesic, you said that scalar function phi is equal I f of r h over r of omega. Can we choose another scalar function?
Say that again, because I didn't visualize the formula.
Scalar function. You choose Schwarzschild geodesic, in which you choose the scalar function. And I ask, can we choose another scalar function?
Another scalar function. I'm not sure if I'm understanding the question, but if you are working with a given theory and a given solution, then the equations are fixed. So you are not, you don't have freedom to change that. You have to change something.
Okay, thank you, sir. So due to shortage of time, we can now take more questions. So once again, thank you for your precious time, and we are looking forward to welcoming you in the future events as well. So
thank you so much for the invitation. It's been a pleasure.
Thank you, sir. So let's move on to the next speaker, Dr. Mohammad Riaz. So.
Hello, everyone. Come to our next speaker, who occurs in top 2% researcher list released by Stanford University, Dr. Mohammad Riaz, Associate Professor, Department of Mathematics, University of Punjab. His main research area is topology and fuzzy theory. He has a long list of achievements, but I will mention few here. He has not only published more than 130 research articles, but also has been reviewer of many reputed journals. Moreover, he is a member of editorial board. Last but not the least, he is an outstanding teacher. The title of their talk is Computational Intelligence and Recent Advances in Fuzzy Optimization. Over to you, Dr. Mohammad Riaz.
Thank you very much, Dr. Taiba Aruj. It is my pleasure to be here with you in this online webinar. And previous lecture was very awesome and very informative for the young researchers in the field of relativity and cosmology. Let me share my talk. Assalamu alaikum to everyone. Today I will discuss a few things about fuzzy optimization related to computational intelligence. I will discuss few topics related to fuzzy set theory. Dr. Taiba, is it clear? You are listening?
Yes, sir.
Okay, thank you. We will discuss fuzzy set, intuitionistic fuzzy set, Pythagorean fuzzy set, Q-rang orthopair fuzzy set, linear Diophantine fuzzy set, linear Diophantine fuzzy topology, and then their applications in multi-criteria decision making. First of all, we discuss about fuzzy set. A fuzzy set is just like a mapping which is called membership function mu from x to 0, 1. The reason is that in classical set or crisp set, crisp set is associated with a characteristic function whose codomain is 2-point set 0 and 1. If the element belong to the set, its characteristic value is 1. And if the element does not belong to a set, its characteristic value is 0. So we have only 2-point codomain 0 and 1. But in case of fuzzy set, we can take value between 0 and 1, any real value between 0 and 1. You can relate with, you can say if a switch is on off, then we have a set. And if you have the device like remote, like you can say dimmer, these are few real life examples to understand fuzzy set, that why we take interval from 0 to 1. That means fuzzy set allow partial membership, partial grading to elements in the universe. Next is the well-known fuzzy set model that is called intuitionistic fuzzy set. In this, we have two membership functions, mu and nu. Mu I of x represent membership degree, and nu I of x represent non-membership degree, with the condition that mu I of x mean membership degree plus nu I of x mean non-membership degree. Their sum is between 0 and 1. Later, Zhu in 2007 and Zhu and Jaeger gave the idea of intuitionistic fuzzy number. This intuitionistic fuzzy number have certain properties like the numbers are triangular number, the numbers are, you can say they have shape like convexity property. For example, if we have a number 0.65 and 0.15, and first number is called membership degree and the second is called non-membership degree, then their sum, you can see it is between 0 and 1. So this is a number, this is opinion, this is evaluation of a decision makers. But in the case if the sum of two values, membership and non-membership, is greater than 1, this number is not intuitionistic fuzzy number. Let us consider an example. We have a set of students in which we discuss the criteria, which is the, you can say, that is a single criteria. Under a single criteria, you can take any one criteria. Under a single criteria, we assign membership and non-membership grade to some students. We have X1 to X5, 5 students, and we have assigned some ordered pairs. These are ordered pairs in the unit square. That means the first component is membership and the second component is non-membership. And these ordered pairs lie in the unit square. And these numbers are intuitionistic fuzzy numbers. For example, if we have an ordered pair, say 0.45 and 0.30, this have a interpretation in real sense that if we relate with the voting example, so we can say 0.45 mean we have 45% votes in the favor, and 0.30 is a non-membership that represent we have 30% votes against, and 25% is the remaining part. This is called hesitancy or abstinence. So an intuitionistic fuzzy number has a real meaning in 3, you can say, categories. You can say membership is in the vote in favor, non-membership is the vote against a criteria, and 25% is the hesitancy. Later, Shen and Tar gave the idea of score function, that if we have some intuitionistic fuzzy number, then to find the ranking of alternatives, we use the idea of score function. And if the score function of two objects is same, then we use the idea of accuracy function. Accuracy function is the sum of the membership and non-membership functions. Later is Pythagorean fuzzy set. A Pythagorean fuzzy set is also the set of ordered pairs in the unit square 0, 1, with the property that the sum of squares of the membership degree and non-membership degree lies between 0 and 1. And later is the concept of Q-rung orthopair fuzzy set. In this, we extend the space for membership degrees and non-membership degrees. And in Q-rung orthopair fuzzy set, we have the constraint that the qth power of membership and qth power of the non-membership have their sum between 0 and 1. So later Liu and Wang gave the idea of score function. This is equal to the difference of membership and non-membership and accuracy function, which is their sum. This is a table which represents some limitations and delimitations of some fuzzy sets. In fuzzy set, we can assign membership degree. You can say you can give a membership grade to alternatives, but it cannot assign non-membership degree. Second is intuitionistic fuzzy set. It assigns membership degree and non-membership degree with the condition that the sum of membership and non-membership degree lies between 0 and 1, because it is always non-negative. So it is equal to 1. But intuitionistic fuzzy numbers and its operational laws cannot deal with the constraint mu plus nu is greater than 1. Later, Jaeger proposed the idea of Pythagorean fuzzy set, in which we have the condition that mu square plus nu square is less than or equal to 1, but it fails to deal with mu square plus nu square is greater than 1. Similarly, the fourth condition is for Martian fuzzy set, in which we have the condition that the membership degree and the non-membership degree, the cube, we take cube of the membership degree and cube of the non-membership degree, and their sum is less than or equal to 1. Later, we have the idea of Q-rung orthopair fuzzy set, which is more generalized, in which we have mu raised to power q plus nu raised to power q less than or equal to 1. And the most generalized model is linear definite and fuzzy set. This is the generalization of all these previous fuzzy sets, and this set covers the drawbacks of the previous fuzzy sets. The reason is that why we extend one fuzzy set to another and then to another, we have a sequence of fuzzy sets. So in order to cover the drawbacks of the existing models, we have to define a new model, and that model will cover the drawbacks of the existing models. Similarly, these are the conditions which we have discussed just now. In intuitionistic fuzzy number, we have constant that mu plus nu lies between 0 and 1. Similarly, in Pythagorean fuzzy number, we have the condition that mu square plus nu square lies between 0 and 1. And the last, linear definite and fuzzy number. In this, instead of taking the powers, we take parameters alpha and beta, and this is the convexity condition that alpha mu plus beta nu lies between 0 and 1, and the sum of the parameters alpha and beta is between 0 and 1. This diagram shows the comparison between these sets. For example, if we take the triangular region, all intuitionistic fuzzy number mu and nu, ordered pair mu nu in the unit square lies in the triangular region. Then we have green line, which is just like a sector of a circle. You can check that mu square plus nu square equal to 1. This is part or sector of a circle. And when we increase the powers, we increase the space. Actually, we increase the space and we give freedom to the decision makers in choosing the membership grades and non-membership grades. But you can check that Pythagorean fuzzy set is the extension of intuitionistic fuzzy set, and then Q-Rang orthopair fuzzy set is the extension of all these, and linear definite ultimately is the extension of all these sets, in which we give freedom to the decision makers in the sense that they can give their own opinion, and their evaluation will be in the whole unit square. We cannot give restrictions to the evaluation of decision makers. Rather, we give their freedom to them. A linear definite and fuzzy set is a model in which assign two ordered pairs. One is mu nu, this is membership and non-membership, and the other is alpha beta, this is the parameters, and both ordered pairs lies in the unit square 0, 1, with the condition that alpha into mu plus beta into nu lies between 0 and 1. And intuitionistic and linear definite and fuzzy number is a number of the form mu comma nu, one ordered pair, and alpha beta is the second ordered pair. This is called linear definite and fuzzy number with these two conditions. Then we go to the idea of linear definite and fuzzy topology and linear definite and fuzzy algebra. To define linear definite and fuzzy topology, we have to define some sets like absolute linear definite and fuzzy set and null linear definite and fuzzy set. In Crisp's set theory or classical set theory, there is a property that empty set is the subset of every set in the universe. So in case of fuzzy topology and linear definite and fuzzy topology, we consider a null fuzzy set or null linear definite and fuzzy set, which will be subset of any other fuzzy set. And there is you can say absolute fuzzy set or absolute linear definite and fuzzy set, and this is the superset of all these sets. So these two sets are very essential to make a topology on these sets. Here is a real life example. For example, medicine or chemicals or compounds used to cure, halt, or prevent disease, ease symptoms, or help in the diagnosis of illness. A combination drug or a fixed dose combination is a medicine that includes 2 or more active ingredients combined in a single dosage form. For example, aspirin, paracetamol, and caffeine is the combination of drugs for treatment, especially tension, headache, and migraine. Let X be the set of some life-saving drugs, and we assign membership degree, non-membership degree, and 2 parameters. One is alpha, which represent good impact against infection, and second is beta, which give us not good impact against infection. This is the tabular representation of linear diaphragm fuzzy set for medication. Another example, we have set of some applicants in which we take the parameters as young and not young. In real life problems, we can take the parameters according to different characteristics. Like we have taken young and not young. You can take, you can say in recruiting problems, we consider PhD degree, we consider not PhD degree, we consider publication, we do not consider publication, we need good communication skill, we need not good communication skills. So these reference parameters have various meanings according to their physical nature. So in the linear definite fuzzy set theory, first we have to develop some algebraic structures as well as topological structures. So these are some operational laws which will define some algebraic properties on linear definite fuzzy numbers, like we take complement, we check equality, we check inclusion, we check union, intersection, sum, product, scalar multiple, and exponents. These are very important operational laws, and by using these operational laws, we can check all other properties, algebraic properties and topological properties. So this is an example. If we have lambda1 and lambda2 as 2 linear definite fuzzy numbers, by using previous operational laws, these operational laws hold the condition of closeness, that these operations are closed within the boundary of the set. Next, we define linear definite fuzzy topology. This is the extension of existing topology, you can say general topology, in which empty set is replaced by null linear definite fuzzy set. The set X itself is replaced by absolute linear definite fuzzy set. We take union, and the union will be linear definite, and then we take arbitrary union, which is you can take by using the above operational laws. And similarly, we take intersection of any 2 members of a tau belongs to tau. So these are conditions of topology, axioms of topology, which are parallel to the existing general topology. So this is an example. We consider lambda omega d1, omega d2, null and absolute set. Similarly, we define interior, closure, and frontier. Then we define the idea of score function. The idea of score function is used for the ranking of alternatives.
Dr. Riaz, sorry for the interruption.
Yes.
We have few seconds for this meeting, so we have to rejoin. You have to join again this meeting.
Okay, thank you.
Okay, thank you.
इसकी क्या वजह है?
डॉक्टर साहब, ऐसे है कि मैंने जैसे अभी बताया, there are different drawbacks and deficiencies of the existing, you can say, decision making procedure. So for example, there is a drawback of existing intuitionistic fuzzy aggregation operators. If one can take any membership degree 0, if a decision maker assign membership degree 0 to one element, then the whole component in the aggregation process becomes 0. So there are different things that in taking aggregation procedures, we have to face various drawbacks, various limitations. So mathematicians are trying to cover the drawbacks of these existing theories. Okay, for example, if we are interested in one criteria, then we consider fuzzy set, and if we are interested in single criteria, and we are in our example, we consider voting against and voting in favor, fuzzy set is better. But there are other fuzzy sets like you can say hesitant fuzzy set. Hesitant fuzzy set assign membership degree according to the criteria. If an attribute satisfies 5 conditions, we assign 5 membership grades. Similarly, if an alternative satisfies 3 conditions, we give 3. So, actually, these extensions of fuzzy set are the need of the today, you can say, real life problems. When we study, you can say, artificial intelligence and computational intelligence, in the background, we see that there are very little things like mappings, like sets, logic. So all these sets and logics are our elementary mathematics, you can say. There are some things like algebraic structures, something like topological structures. So you can say that we have some problems, and according to their solution, we go to these sets.
I agree with you, totally I agree with you, but my question was that a situation including some kind of randomness has not been controlled by the fuzzy theory till now, or may not be controlled. I want to take a guideline on this direction. If the situation has some kind of random influence, then how would we control using these concepts?
I understand your question. Actually, अब जब आप randomness और fuzziness को consider करते हैं, अब randomness क्या है? You can see that कि एक event है, वो occur करता है या नहीं करता, ठीक हो गया? अब वो occur करता है या नहीं करता, हम उसमें occurrence और उसके events और उसकी possibilities की बात करते हैं, ठीक है जी? लेकिन जो fuzziness है, वो ज्यादा broad spectrum है. फजीनेस जो है उसकी ऑल पॉसिबिलिटीज को भी डिस्कस करता है कि उसकी अक्रेंस है नहीं है, तो उसको फिर आगे हम उसको किस तरह से कैटेगराइज करते हैं अकॉर्डिंग टू द क्राइटेरिया. और फजीनेस की ये प्रॉपर्टी है कि हमारे पास जो भी ऑल्टरनेटिव्स होंगे और जो भी क्राइटेरिया होंगे, वो उनको फिर उसकी एक्चुअल जो रैंकिंग है वो असाइन करेगा या ग्रेडिंग असाइन करेगा, ठीक हो गया? सो ये जो मॉडल है ये रैंडमनेस से ज्यादा स्ट्रॉन्ग है. तो इस पे काफी लिटरेचर ऑलरेडी मौजूद है. फजी ऑप्टिमाइजेशन पे ना बुक्स है, बहुत अच्छी बुक्स हैं, तो उसको देखा जा सकता है इसमें.
Thank you so much, sir, for your very satisfying answer.
Thank you.
But we have limitation of time. That's why, once again, thanks very much. Now over to you, Dr. Sarish.
Okay, thank you, Dr. Riaz, for such a good presentation. So our next speaker is Dr. Faisal Javed, who is a postdoctoral fellow from Zhejiang Normal University, China, and he will talk about study of thin shell wormholes with non-linear electrodynamics. So, please check. Assalamu alaikum, Dr. Faisal.
Yes.
Please check. Can you share your screen?
Okay. Okay, it's clear.
Okay, good.
First of all, thank you for the invitation. The topic of my talk is stability of thin shell wormhole with nonlinear electrodynamics. Okay. The plan of my talk is gravitational flat. Then I move towards thin shell wormhole and the construction by using the junction conditions. And then I move towards research work and some concluding remarks. Basically, Stars are giant and luminous sphere of plasma that held together by its own gravity. And initially, the stars are in hydrostatic equilibrium due to the pressure generated by fusion reaction on the surface of the star. And a star preserves its equilibrium position if the outward directed pressure of the fluid and the inward gravitational force counterbalance each other. As shown in this figure, here the gravity and the surface pressure counterbalance the effect of each other. This equilibrium position is disturbed when the inward gravitational force becomes dominant as compared to outward pressure of the fluid. When this happens, this gravitational collapse of a star is happened, which is the construction of astronomical objects due to the influence of its own gravity. We tend to draw matter inward towards the center, which is a fundamental mechanism for the structure formation in the universe. And the final outcome of gravitational collapse are referred as compact objects like white dwarfs, neutron stars, and black holes. And basically, the formation of these compact objects depends on the limit. If the star having mass smaller than the Chandrasekhar mass limit, which is 1.4 times mass of the sun, then the final outcome of gravitational collapse is white dwarf. White dwarfs are composed of degenerate electrons, which produce enough pressure to resist the gravitational collapse. And if the star having mass is in between 1.4 to the 10 times mass of the sun, then the final outcome is neutron star. And neutron stars are also composed of degenerate neutrons which produce enough pressure to counterbalance the gravitational force. And if a star having mass greater than 10 times mass of the sun, then it leads to a black hole. Black holes are very interesting compact objects for their geometrical structure. And no, I move toward the geometrical structure of black holes. First, I will explain the event horizon. It is a boundary defining the region of space around a black hole from which nothing can escape, not even light. And a singularity is a location in space-time where a black hole has infinite gravitational field. It is a place where all mass of black hole is composed. Now I move towards the wormhole structure. A wormhole is a solution of field equation which acts as a shortcut associated distant region of the space-time through a handle or tunnel. Basically wormholes can be characterized into two categories. One is a non-traversable, another is reversible. A wormhole that does not allow two-way motion, which is also known as non-traversable wormhole, and it is named as first non-traversable wormhole is Einsteins Theory, which is suggested by Einstein in 1935. And a wormhole which allows the observer to move freely in both directions from one region of the universe to the other one is known as traversable. In order to check the viability of physical model, some restriction must be imposed on the physical model, which is also known as energy condition. And there are well-known energy conditions like null, weak, strong, and dominant energy condition that depends on the energy density and pressure of the fluid distribution. Mathematically, these energy conditions can be for normal matter distribution, these energy conditions are very okay. It's clear?
Yes, now.
Okay, thank you. Okay, for normal matter distribution, these energy conditions are verified, while for exotic matter, null and weak energy conditions are violated. No, the Morrison found that exotic matter could help to formulate the reversible wormhole. And we introduced a cut and paste technique to construct a thin-shell wormhole to minimize the usage of exotic matter from a suitable geometry like Schwarzschild black hole. The exotic matter was restricted at the edges and corners of the wormhole slot. Now I move toward the geometrical structure of a thin-shell wormhole. Basically, for thin-shell wormhole construction, we choose two geometries like M plus is a exterior manifold and M minus is an interior manifold, and symmetry represents the hypersurface. These manifolds are connected at the hypersurface by using the junction conditions. Here, like the final outcomes of these matching, here sigma represents the energy density and P is the surface pressure of the matter distribution located at the junction surface. Now I move toward the junction conditions. There are many cases in which one solution of field equation is not sufficient to describe the entire solution, like interior Schwarzschild interior solution. If we choose interior solution as a Schwarzschild and exterior solution is a Schwarzschild, then it represents a final structure essential wormhole. If we choose inner is our d theta space time and exterior black hole space time, then by using the mother Mottola concept, it represents the gravastar structure, and there are many matching conditions and the final outcome structures. These conditions allow the smooth matching of two regions of space time, like interior and exterior separated by the hypersurface, to form a valid solution of the field equation. Now, basically, to understand the junction condition, I will explain some basic definitions. First one is integral curvature, which is the deviation of a surface from the flat geometry within the whole surface, and mathematically it can be expressed as where G mu is a metric tensor and X mu represents the coordinates of manifold. And second one is the extrinsic curvature. The curvature of surface which is embedded in a surface of one more dimension is called extrinsic curvature, where n beta represent normal vector and xi represent the coordinates of hypersurface. There are two well-known junction conditions, and first one is the Jordan's junction condition, which states that the condition for the smooth matching implies that the induced metric and the extrinsic curvature must be same on both sides of the hypersurface. And mathematically, it can be written as first equation represents the line element of interior, exterior, and at the hypersurface must be equivalent, and second represents that the extrinsic curvature of interior and exterior space-time and must be equal, and their difference must be equal to 0. And so the second is the Israel junction condition, which is due to the thin layer of matter at the surface, which gives the failure of Darmus junction condition due to the discontinuity in the extrinsic curvature. And mathematically, it can be expressed as here. This condition shows that due to matter distribution at the hypersurface, by the joining of interior and exterior space-time, the extrinsic curvature of both manifolds does not equal to does not the same. So their difference is not equal to 0. So its difference must be some constant, maybe some another quantity, and which is here noted in kappa ij. No, basically the dynamical configuration of thin shell is depends on such matter distribution, and basically energy density and pressure of such matter distribution can be evaluated by the reduced form of Einstein field equation, which is also referred as Lenz's equation. And this equation mathematically can be expressed in this form, where kappa is defined the following form case, and this equation laid the discontinuity in the extrinsic curvature to the surface energy momentum tensor. Now I move toward the equation of state. Basically, the matter located at thin shell must follow some equation of state, which plays a major role to discuss the stability and dynamical evolution of thin shell and thin shell wormhole. And next one, basically stability, the ability, which is the ability of an object to return to its original form against applied forces. It means that behavior of the system does not change drastically under small disturbance. For example, this figure explains the stability of a simple object. Here, first position it is in the stable. After small perturbation, this particle maintains its original position, while second position is unstable. After small perturbation, it does not maintain its original position. Now I move towards my research work. Here I choose the line element of charged black hole with non-linear electrodynamics, and the respective metric function is given in the following form. Here alpha is a coupling constant, m is a mass of black hole, and q is the charge. When alpha equal to 0, it reduces to Rn black hole, and in the absence of alpha and q, it is reduced to Schwarzschild black hole. For construction, we choose the parametric equation of the hypersurface, which is here r is the radius of the thin shell and tau represents the proper time. Sorry. The corresponding induced metric at the hypersurface takes the Pauling form, and the respective normal factors for both surfaces can be expressed in the following form, and the corresponding components of exchanges of our interior and exterior spacetime are calculated as follows. And the Lang's equation by using these equations gives the following result about the energy density and surface pressure of the fluid. Here dot represents the over dot represents the proper time derivative. Now we consider that a thin shell does not move in the radial direction at equilibrium shell radius. So radial derivative of the shell radius must be 0 at okay, these plots, it is clear. Exercise. Hello. Are you listening?
Yes, Dr. Faisal, we can hear you.
Okay, thank you. Okay, this plot shows the energy conditions of wealth structure by using energy density and surface pressure for suitable values of physical parameter. And it is found that the matter distribution at thin shell violated the energy condition, and which is viable for the construction of thin shell. And this matter shows that this type of fluid distribution and construction is suitable for the observer movement from one region to another. Here, now we consider the value of the energy density and effective potential of the constructed developed structure. Here, by using the equation of quotient, where r dot square equal to omega, where omega is the effective potential of the developed structure. Mathematically, it can be expressed as in equation 13. And for stability analysis, we consider the static shell radius or not and expand the effective potential about equilibrium shell radius by using Taylor series up to second order term. And for equilibrium configuration, above equation can be expressed in this form. Here, second derivative plays a major role to discuss the stable and unstable configuration of this structure for suitable equation of state parameter. And it is noted that rho and p obey the conservation equation, and mathematically conservation equation are given in this form, and the exact solution of conservation equation depend on the choice of matter distribution, which can be described as. And for different matter distribution, it behaves like different, like barotropic, quantum, Chern-Collision. And for every choice of equation of state, it behaves, and stable configuration or dynamical behavior are different. No, the second derivative of potential function for generalized equation of state can be written in this form. Here, gamma naught is a radial derivative of surface pressure, and the beta naught is the equation of state parameter, also referred as beta count parameter. Now here I choose the barotropic equation of state to discuss the stability of thin shell wormhole, where omega was the equation of state parameter, and the respective by using the conservation equation, the surface energy density are given in this form, and the respective effective potential turns out to be in this form, and its first derivative with respect to shell radius by using the equation of state parameter, and the second derivative of potential function by using conservation equation and our model parameter, it turns out to be in this form. Now, Now it is noted that first the radial derivative of friendship function at equilibrium chart reveals its vanish for particular value of megawatt pi, and for particular value of here I choose omega equal to -1. We have the shell radius approximately in this form. And now I observe the behavior of our potential function in the absence of coupling constant and charge, and which reduces to Schwarzschild black hole. And it is found that second derivative is basically shows negative behavior, and it shows the unstable structure for such type of matter distribution. So, and for Rn black hole, this color shows the unstable behavior. Here, second derivative shows the basically only negative behavior for any value of charge and mass. So it means that Schwarzschild black hole and Rn black hole shows the unstable configuration for barotropic equation of state. Now, I observe the behavior of nonlinear electrodynamics on the stable configuration of thin shell wormhole. Here it is found that three colors, one is blue is for second derivative equal to 0, and brown represents the second derivative is greater than 0, and this color is represent the a less than. So it means there is a possibility for the stability of developed structure. So it's mean if we choose the coupling constant and mass in this range, then we found the stable configuration. Otherwise, Schwarzschild and Rn black hole completely shows unstable behavior. So by choosing these ranges of coupling constant and mass, we plot the second derivative of partial function and found the stable configuration as it shows positive behavior, and the stability also enhances for negative values of coupling constant. So our system shows stable behavior for barotropic equation of state in the presence of nonlinear electrodynamics. Now I move toward the second equation of state, which is quantum-like variable equation of state, where W is the equation of state parameter, and the respective energy density and potential function and its equation of state parameter values are given in this form. And it is found that for such type of matter distribution, system shows more stable behavior. Here, basically, this system involves the shell radius. It is also known as variable equation of state because it depends on the shell radius, and here any constant, and it is found that as n negative, and for different values of alpha it shows basically positive, stable, unstable, and neither stable nor unstable solutions. So it is found that basically for such type of matter distribution shows more stable behavior as compared to barotropic equation of state. Now I move towards some conclusion. Basically, thin shell wormholes have been constructed through the matching of two equivalent copies of Rn black hole with nonlinear electrodynamics, and the developed structure is physically acceptable for the wormhole geometry as null and weak energy conditions are violated. And the stability of developed structure has been explored by using radial perturbation with barotropic and quantum-like variable equation of state. And it is noted that wormhole geometry developed from Schwarzschild and Rn black holes express unstable behavior for every choice of physical parameter for barotropic equation of state. Hence, the presence of nonlinear electrodynamics provides stability of wormhole geometry for barotropic equation of state. And for quantum-like variable equation of state, thin shell wormhole with nonlinear electrodynamics is more suitable for stable configuration. Thank you.
Okay, thank you so much, Dr. Faisal. So
Yes.
I guess there is no question. So let's move on to the next speaker. I think over to Dr. Taiba. Thank you, Dr. Faisal.
Okay, thank you.
Okay, our next speaker is Dr. Hafsa Rizwana Kausar, Dean Faculty of Science and Technology, University of Central Punjab. Her main area of research includes gravitational and cosmology. Her title is Unfold the Universe via Relativity. Please welcome Dr. Rizwana.
Hello. Assalamu alaikum, everyone. I hope you can hear me well.
Yes, we can hear you.
Thank you. And good morning, good afternoon, and good evening, everywhere you are, the international participants. Thanks to Dr. Sarish and Dr. Rubar for asking me to speak on the topic of my convenience. So I was just looking at my previous talks presented by other speakers, and I was thinking they have talked about the latest research and they move forward, and I am moving back. So I have chosen intentionally this topic just to refresh the concepts of the relativity among the researchers, the students in the community. So let me share my screen. Yes, just a minute. So the topic is unfolding the universe via relativity. The first question which come into mind among the layman, that what is relativity? So relativity means something, there are two definitions, maybe one informally and one is formally. So if I look at the informal definition, we think about that is something that is moving, or that is something relative. My mother, aunts, my mother's cousin, my first cousin, my uncles, and so and so on. This is with reference to some of the relationship that is maybe known as a relative. So this is the same thing that is with the relativity, that is something about the moving objects, and but with reference to some of the and other objects. So since everything is moving in this universe, so everything is relative of each other or relative to each other. So that is the informal definition, that since everything is moving, so everything is relative to behaving one another. So if I look at ourself, that where I am standing, I am not standing, I am rotating about myself. That is I am, if I am sitting on the earth, I am rotating about my own orbit. And if I look as an external observer on the earth, I can see that our earth is moving in some of the other orbit around the sun. So as an external solar system, if I look at the solar system, I can see that the whole solar system is moving around some of the galaxy. So the same story is applicable to all the Earth and then to the solar system, then the neighborhood solar system, then the galaxies and clusters, superclusters, and then so and so on. So since everything is moving in this universe, so we can say that nothing is absolute in this universe, that no measurement at all in this universe is absolute. So if we go for the formal definition, if I ask the question to my students that what is a relativity, and you have the answer. Informally, they can give the answer correctly, but for the formally, they need to immediately go for the Google. When they take the help of the Google, there is the definition which comes up, that is a theory of relativity, usually encompasses two interrelated theories by Albert Einstein, special relativity and general relativity, proposed and published in 1905 and 1915 respectively. Special relativity applies to all physical phenomena in the absence of gravity, and general relativity explains the law of gravitation and its relation to the force of nature. It applies to the cosmological, astrophysical realm, and including the astronomy. So if I sum up all these a few lines, it means I need to understand few of the concepts. The first question, that maybe who is the Albert Einstein? And then what is the special relativity? It means something without gravity. If there is no gravity, where it is, that is vacuum. And then again, the general relativity, that is something dealing with the gravity, with the sum of the force, and that is in the nature. That we are talking about the natural world. And then coming to the application of the general relativity, if we are learning the relativity where the applications are, the students ask the question that its application are on the cosmology, study of the universe, astrophysics, the study of the physical processes happening in the stellar objects, and astronomy beyond in the solar system and beyond the galaxy. So that's basically the layout of my talk. That is, first of all, I step-by-step introduce you by Einstein and what is the special relativity, and then moving to general, and then what are its applications shortly. So this is the cutest child. This is Einstein, and this is the time when he discovered all the relativity, and when he was so popular among the community. That is this is the Einstein. So he was born in Germany in 1879, and he got his PhD from Zurich University, Switzerland. And in the same year, he published his 4 ground-breaking papers in relativity at the age of only 26. So I am just comparing our students, our graduates, which are getting their degrees, what revolution they are bringing in the community. And he has a different nationalities, American, German, and Hungarian, and the Swiss. At the age of, at that time, his age was 76. So this is the Einstein Museum. Once I visited in the Switzerland, where it was showing that it is his house is there. And I took pictures from different places of his museum. This is a space-time they have created, and there is a pathway. When someone moves, there are different pictures of the Einstein placed over there. And this is also the space-time representing. And this is a few of the pictures of the study room. And then again, a room, living room, and you can see here the pictures. And this is all about the Einstein. So the next question which comes in the mind, okay, if he conceived 2 theories, theory of special relativity and general relativity. So special relativity is defined that without gravity. So at least we should know what is a gravity. Gravity is a force by which 2 bodies attract each other if they have some mass. So more gravity, more pull and more attraction is between. If there is less gravity, it means it has a less mass and less attractive power. Similarly, this is the concept of the Newton about the upper, we call it, and all the planets are moving in a very organized way. This is the gravity which is holding all these planets in their own orbits. So coming to the special relativity, Einstein's special relativity deals with the relationship between the space and time and laws of physics in the restricted frame of references, that is inertial frame of references. As I said, I am thinking that there are maybe some of the students which are not from the area of the relativity. So just to focus that, first question comes in the mind that what are the reference frames? And then what is the space-time and what are the postulates of the special relativity where it is built on? So the space, what are the frame of reference? It is a point from where an observer can observe the event. For example, we are sitting on a ground and we are observing sun. This is our frame of reference. If we are moving in a plane and we are observing something, the plane is a frame of reference. And if there is some spacecraft and someone sitting in the spacecraft, he's observing something, that is a frame of reference. That is, it is what an observer is standing, sitting, moving. So the first postulate of the relativity was the laws of physics are same in all the inertial frames. In fact, the story this postulate can be understood well by thinking that this guy is sitting on the ground and he's looking at a bowl of some of the pieces, stone pieces, and he can observe. So what happened?
Dr. Rizwana, please continue.
From where? I couldn't understand where the connection was lost. From here?
Dr. Rizwana, from here.
Okay. So I was talking about the first principle of the relativity, that is of relativity as well as of the special relativity, the laws of the physics are same for all the observers observing from the inertial frames that it may be in the static position or moving with a uniform speed. The second law is the speed of light is constant for all the inertial frames in vacuum. So to understand the principle of the invariance of light speed, we need to understand the Maxwell experiment, Michelson-Morley experiment, as well as the Newton's law of the physics. So the understanding of behind this principle is that if we move to if we stay in the Newtonian physics, there is a problem. That what the problem, if there is a rocket is moving and inserting some light in the same direction, that is the observer in this rocket can observe speed as c minus 0.9 c. See, if there is another inertial frame that is moving with the 0.9 speed, but another in the upward direction, he observed with the 0.9 c plus c. And another spacecraft which is coming from the opposite side and it is moving with the 0.8 velocity, then the observer sitting in this spacecraft, although it is moving in the inertial frame, he observed as the plus its own speed as well as the speed of the coming from the opposite direction and the speed of the light. So we can see that since all the frames are inertial frames and they are moving at the constant speed, but why they are observing the different speed of light? So that is a contradiction. However, the Maxwell states that light is constant, and his experiment or Michelson-Morley experiment was stating that speed of light in the vacuum is constant. So believing that Maxwell's experiment, we suppose that since all the frames are inertial, so everything, every observer will observe the speed of light at the same speed, that is the 3,000 kilometers per second. So this is the second law of relativity. Now the third is the come up the space-time. That is, what is the space-time? The idea comes that type is not absolute. And from where this idea comes, that is from the second law of the special relativity. So for this, I have a video demonstration. Maybe I can skip few of the parts, but I want to show few of the parts of this video that you can see here. That how time dilate.
Albert Einstein, then a mere patent clerk in Bern, after trudging through his day's work, decided to board a tramcar on his way home. Einstein would often wrap up his work as soon as possible to contemplate the truths of the universe in his free time. It was one of these thought experiments he devised on that tramcar that revolutionized modern physics forever. While receding away from the Zeitglocke clock tower, Einstein imagined what would happen if the tramcar were receding at the speed of light. He realized that if he were to travel at 186,000 miles per second, the clock's hands would appear to completely freeze. At the same time, Einstein knew that back at the clock tower, the hands would tick along at their normal pace. For Einstein, time had slowed down. This thought blew his mind. Einstein concluded that the faster you move through space, the slower you move through time. How is this possible? Einstein's work was heavily influenced by two of the most iconic physicists of all time. First, there were the laws of motion, discovered by his idol, Isaac Newton. And second were the laws of electromagnetism, laid down by James Clerk Maxwell. Newton's laws insisted that velocities are never absolute, but always relative, so that their magnitudes must be appended by the phrase, with respect to ideas of Newton and Maxwell, can be demonstrated with another of Einstein's brilliant The Speed of Light. If the speed of light can witness the lightning strike simultaneously, a measurement of the speed of light, Einstein had to make a difficult choice. Either Newton's laws were incomplete, or the speed of light was not a universal constant. Einstein realized that the two notions could coexist with a small tweak in Newton's laws. To get rid of the discrepancy in the measurements, Einstein suggested the time itself for the man on the train.
Dr. Rizwana, is it a video or just audio?
Such that the magnitude remains a constant.
We cannot see the video.
All this absurdity.
And you can see the slides.
Only the slide is stuck, I think. Live experiment for time dilation.
Time moved unflinchingly in a single direction, forward. Einstein, however, had just realized that time
So you can't
stretches
see
and
the
contracts,
videos
varying
moving
with
forward?
velocity.
No, it's just audio.
Oh. So I think there's a going back experience. So. So now you can see this slide.
Yes, slide 21, space-time is not absolute.
Yeah, okay, we can continue with it. The idea behind is the why space-time and why time is not absolute. So the idea comes up from the second principle of the relativity, that if the speed of light is constant, then there is something happens on that at the end of the time. If we take all the laws of the physics are same. So if something is moving at very high speed, just close to the speed of light, then time slows down, it stretches. So it is a live experiment which is performed by some of the scientists, and when they send a clock on a spacecraft and move around the Earth for 2 times on the higher speed, then they observe that there is a minor change in the time, and as compared to the time clock placed on the Earth. So we can say the time time slows down in the space when it is with the accompanying something moving at a very, very high speed at close to the speed of the light. So there are the few consequences of the special relativity, that time slows down and length contracts and the mass energy equivalence and the twin paradox. But remember, time dilate, length contracts and mass energy are equivalent at the higher speeds, and then there is a twin paradox that is very known for those who knows the relativity, that if some there are two twins and some is staying on the Earth and some is moving at the higher speed, and it has a short life, and the person sitting on the Earth has a more age. So but all these consequences, remember, only exist applicable at a very, very high speed, close to the speed of light. So for us, maybe not it is realistic, and maybe because this is an inertial frame that is in the vacuum, but with the one condition, that is very, very higher speed, close to the speed of the light. So for this is a very important concept to understand, that why the laws of gravitation and where the Newton's laws of gravitation are applicable, as we understand that the first law of the special relativity, that all the physics laws are the same in the inertial frames. In fact, relativity describes those situations where either bodies move at a very higher speed, close to the speed of light, or gravity is very, very high, very strong, or both of the conditions are there. However, Newtonian theory and relativity coincide when there is a low speed and low gravity. So now coming forward to the general relativity. Again, if I move to the general relativity, is also known as a general theory of relativity, is a geometric theory of the gravitation published by Albert Einstein. Here is a new terminology that is a geometric theory. So it means it is something about the geometry as well as the gravitation. So if we take the example of the trampoline and we put some of the heavy mass on it, we will see that if we sketch a line and it bend towards that mass. In the second figure, you can see that sun has a more mass, so it has a more curvature, and similarly Earth is as compared to less, and Moon is negligible as compared to the sun. So they have accordingly they have the curvature around it. So that is the idea, that if there is a mass, there is a curvature around, that is geometry exists around the mass, momentum and energy. So the Einstein's achievement of relativity is to build up this field equations, that is r mu nu minus 1 by 2 r g mu nu is equal to 8 by g t mu nu. This is the constant, and this is a tensor, that is energy momentum tensor, and this is the curvature of the space-time, which is explaining the geometry of the matter. So if I expand these field equations and vary from 0 to 3 to both the indices, we have a system of the 16 field equation. So that is actually the achievement of the Einstein. He developed these field equations and opened the research for all the researchers to have many of the PhDs and MPhil in this area of research. So to understand the field equation, you need to understand the concept of the tensor calculus, differential geometry, and then coming to the tensor differentiation, covariant derivative, and some of the concepts which are involved in this field equation, that is a metric tensor, Christoffel symbols, Riemann tensor, Ricci tensor, and the Ricci scalar. The metric tensor is a quantity which captures the geometric and causal structure of space-time. In fact, it measures the distance, volume, angle, and curvature at some of the manifold. So it has again the 16 components, and for if the space-time is flat, then it reduced to the diagonally Minkowski space-time. So again, this is a Christoffel, and he provides the notion of the covariant differentiation, in which generalizes a classical direction derivative of a vector field on the space-time. So all the information about the space-time structure is being contained in the metric. So it needs to be expressed Christoffel symbol in terms of its metric. So first concept in the relativity comes from the metric tensor, and then it used to establish the Christoffel symbols. You can see each and every index of the Christoffel symbols denoting some of the geometry as well as connecting the physics of the space-time. And again, then by using the Christoffel symbols and the metric tensors, we formulate the Riemann curvature tensor, which actually tell us the measurement between the effect of the two parallel curvature moving along the two different curves. That is a Ricci tensor and Ricci scalar. In fact, they can be retrieved mathematically from the Riemann tensor by contracting along with the metric tensor. However, it in fact tells the convergence or divergence of the two vectors. If we have a sphere, we can see that the curves are the converging, and if we have the hyperbola, they are diverging, and if we have a plane space-time, it moves parallel to each other. So this is the energy momentum tensor. Energy momentum tensor has again the 16 components, and it helps to create, or it helps to understand the effect of the force on the geometry, that it is the source of the gravitational field. So you can see the first component is energy density, and then energy momentum density, momentum flux, and the shear stress and the pressure. All these components are absorbed for a matter in the form of the gravitational field. So ultimately, we achieve these Einstein field equations, which describe the different parts of the space-time, how the distance moves, how the vectors behave, how the curvature behave, and how the matter behaves. And it is, in fact, the ultimate goal to solve these field equations. So the solution of the field equation leading to different type of areas like astrophysics, astronomy, and the cosmology. So the one of the, I think the first author has covered some of the things of the gravitational waves, and that is the application of astronomy, and one has covered the gravitational collapse, astrophysics, and also it is applicable to the cosmology to understand the universe model. For example, how galaxies are behaving, how getting far away from each other. Either universe is overall static, or the expanding, or like, so all these applications we can understand the universe through the general relativity. And this is about the gravitational collapse. All the stars which we look at the sky, ultimately they have to collapse catastrophically within few seconds. It is done when the gravity failed to balance the pressure, and it collapsed in the form of the black hole, white dwarf, and neutron star. So, and there is a question comes in mind, when our star would collapse. So our star, they have different phases, and now we are here. Now we are here, then gradual warming, if we can feel there is a gradual warming on the earth as well, and then it become a red giant, and ultimately it collapse and become a white dwarf, and that is a signal in the end of the life on the earth. So there is a fear that when this happens, it's so far, relax. And it will happen in the 5 billion years after now, the sun will begin to die. The gravitational waves are this concept is that if something is moving, it is emitting some of the curvature waves in the space-time. So if it is heavy, something heavy like the black hole in other galaxies moving, it is emitting some of the waves. And then when the waves reaches us, they can be observed by the gravitational waves. So there are all the waves are moving at the speed of light, and usually these gravitation shows that there are some binary pulsars are happening in the universe and they are revolving each other. So luckily for us on Earth, while the origin of the gravitation waves can be extremely violent, by the time the wave reaches the Earth, they are millions of times smaller and less disruptive. As per the gravitation detected from the LIGO, the amount of space-time wobbling they generated was thousands of times smaller than the nucleus of an atom. So it's not hurting, it is not, you can observable by us. So there are two sensitive interferometers which are placed in that is LIGO and the Virgo, that is in the Italy and USA, which having the antenna's length of 4 kilometers and 3 kilometers, both have detected the gravitational waves. That is the check of the Einstein theories of relativity. And that's all. Because it's a short of time, you can ask any question, please, if you have.
Thank you so much, Dr. Rizwana. So any questions from the audience?
I think there's no
I think there is no question.
Yeah.
So, okay.
Hello.
Jiji walaikum assalam. Zaim is there, I think so.
Actually, I want to ask how we are going to enter in the geometrical shape of the energy. That an object can be translated to one place to another. But how we will be able to know it will be converted into energy form regarding the equation of Einstein is equal to mc square.
E is equal to mc square. How energy math is converted to energy, that is at the speed of light. It's a very something moving with the speed of higher at the close to the speed of light. Then with the relationship of the speed of light, energy mass is converting to a lot of energy because it is with the speed of the light.
Oh, I think there is no other questions. So let's move on to the next speaker. Dr. Zaimul Haq Bhatti. He is Associate Professor, Department of Mathematics from University of Punjab. And his main area of research is gravitational and cosmology, mainly focused on gravitational theories and dynamical instabilities. And he's ranked among the top 2% scientists from all over the world. So welcome, Dr. Zaim.
Thank you very much, Dr. Sarish. I am audible to everyone there?
Yes, Dr. Zain, you can
Thank you very
share
much.
your slides.
Thank you very much, Dr. Sarish. In the name of Allah, the most beneficent, the most merciful. First of all, I would like to thank particularly Dr. Sarish Iftikhar for inviting me in this 2 days international webinar on recent trends in applied mathematics and physics. So keeping in mind about the webinar on recent trends, I will talk about some structure scalars and their evolution. So according to that title, we have some words like structure and scalars and the evolution. And according to the word scalars, we have in mind like vectors, scalars, tensors, etc. So here it means for scalar functions, we have to each point in space that corresponds some such scalar functions. Then we can say that a scalar field has been defined. And the evolution means the evolution of the universe and how the mathematics related, which can explain the evolution of the universe, is related with the structure formation or the equations describing the structure formation of our cosmos. So there are particular scalar functions which are named as structure scalars, which has been recently obtained from the orthogonal splitting of the Riemann curvature tensor. And these were introduced in the discussion about the structure and evolution of self-gravitating celestial objects. And such scalars were shown to endowed with a distinct physical meanings. So to start with, we have different questions in mind about the universe. That is, how did it begin? How is it organized and held together? What is it made of? And how is it changing? So these are the questions related to the universe. And to answer these questions, we have in mind different theories about the evolution of the universe. The theories of the universe include the general theory of relativity and the theories related with the quantum mechanics. I will explain general theory of relativity later on, but to some point, I will explain that general theory of relativity basically describes some big structures, masses, and energies of the stellar objects, while quantum mechanics deals with small structures which include masses and energies at atomic and subatomic levels. So related to the general theory of relativity, the most important part is the gravity. And the question is, what is gravity? Gravity or gravitation is a natural phenomena by which objects with mass attract one another. Also, it is a force that causes things to fall when they are dropped. The force of gravity gives things their weight. Every object has its own force of gravity. That is, if we have different objects, then they might have different forces of gravity. The gravity depends on the amount of material that makes up an object. The more material an object has, the stronger is its force of gravity. The force of gravity between two objects decreases as the object gets farther apart. Isaac Newton was the first one to discover the law of gravity in the 17th century, and he stated that any two objects or particles having non-zero mass, the force of gravity tends to attract them towards each other. Basically, Newton was the first one who introduced the concept that only mass is responsible for gravitating effects. But Einstein introduced the concept that not only mass and energy, but all sources of energy and momentum are responsible for gravitational effects. So he introduced another theory, which is named as general theory of relativity. So there is an important question that we can see gravity. So the answer is no, we cannot see gravity. So when a man wants to parachute out a plane, he falls down towards the ground because of gravity. Also, when a man ascends towards a mountain, he feels that he is tiring up. That is when he is moving against the gravity. When he descends down, we don't feel tired. So when walking on the earth, this is the natural phenomena. We are feeling the effects of gravity. So what happens in case of absence of gravity? Life on Earth will be impossible without gravity. A big mess is the only description of our Earth in case of absence of gravity. So is gravity same over the Earth's surface? No, it turns out that in some places you will feel slightly heavier than other objects. Another question about gravity is that if light is affected by gravity, the answer is yes. Light is affected by gravity, but not in its speed. General relativity gives two descriptions about the effects of gravity on light. That is, the first one, it can bend light. That is the bending of light, which includes effects such as gravitational lensing, That is the gravitational lensing. Basically, when light moves, it warps the space-time around the matter which is causing it. So what the light beam sees as straight is not straight to an outside observer. And the second effect which is observed by the outside observer is that it can change the energy of light by shifting the frequency, and famously known as the gravitational redshift, not by changing the speed of light. So the speed of light is still constant for observers observing the light. What about gravity and astronomy? Astronomers say that all the planets have gravity that attracts the nearby bodies, and the force of gravity is proportional to the mass of this planet and the distance between it and the bodies that it attracts. So that all the cosmic bodies like the sun, moon, planets, stars, and cosmic dust, etc., they all have some influence of gravity and all have their own gravitational fields. So Earth's gravity keeps the moon on its path around the sun. Before, when Einstein introduced the concept of general theory of relativity and he predicted the phenomena of gravitational waves, this is predicted, this is basically checked or tested after 100 years of his theory of relativity. Before this, we have the phenomena or conception that everything which we see, which we can understand, is the waves which is due to the electromagnetic natures. But now we have the influence of gravitational fields of one object to the another object. So the question is gravity equal in all planets? No, the moon has its own gravity, but it is not as strong as that of Earth. That is why astronauts on the moon can carry equipment that would be too heavy to carry on Earth. On Earth, you might be able to jump 3 feet, almost 1 meter. On the moon, which has low gravity, you might jump up to 20 feet, 6 meters. On Jupiter, which has high gravity, you could jump only 14 inches, that is 35 centimeters. So this is the pictorial representations of the jump showing here on Earth, on the moon, and on the Jupiter. Fun in space, an astronaut who finds juggling fruit is easy without Earth's gravity pulling it down. Therefore, the Earth has gravity field that attracts people to it. And because of this gravity, the objects are settled on the Earth's surface, even in the atmosphere. So this means that if there was not a gravitational field for Earth, the atmosphere would have escaped and faded away in the outer space. Hence, the gravity is the reason for the stability of life on the Earth. So this is the basic part of the theory of relativity, which was predicted by Albert Einstein. And this was the second theory as discussed by Dr. Izwana, that is the general theory of relativity in 1915. The later part, the earlier part was a special theory of relativity, which have no influence of general theory of, which have no influence of gravity. So according to which the mass of the heavier object created curvature in the space-time. That is we can't differentiate between the effects of curvature and the effects of gravity on the sphere. So for instance, if we can replace this mass by another mass of the same quantity, then the thing which is moving around this particular mass will follow the same curved path. Like the beautiful pictorial representation of the sun, that Earth is moving around the sun, and the mass of the sun had created a dimple on the space-time, and the Earth is moving around that sun. So this is because that the mass of a particular object, namely sun, has created a particular amount of curvature, and and we can say that gravitational effects have been created with that particular amount of geometric object. So the Earth is following that particular path. And Einstein presented this field equation to describe the evolution of our universe in order for the universe to be in the static form. Here, G mu nu is basically representing the Einstein tensor, which actually represents the geometric part, while right hand side is the matter part. And this matter part is basically related with the geometry in defining that how much matter has created how much curvature in the space-time. These are the shortcomings of general theory of relativity, which includes that general relativity is unable to discuss the mysterious dark constituent of the universe, and it predicts black holes. Black holes are basically the singularities as explained by Professor Almo in his talk, where all laws of physics fail down. So it has its own drawbacks, general theory of relativity, and we need to move forward to modify or upgrade the train of this general theory of relativity. So what are the modified gravity theories and why we need modified gravity theories? So modified gravity theories are basically used to describe the current nature of our universe. And these are basically the modification of general theory of relativity. So these theories discuss the stability of celestial objects better than that of GR, and these theories address both dark energy and dark matter better than that of GR. These theories explain late time acceleration of our universe. This is the diagram which was presented by Tisa Baker, that what are the modified gravity theories. These modified gravity theories include non-local theories, higher order gravity theories, higher dimension gravity theories, and which can include some basic field content, which can link with scalars and vectors, etc. The higher order gravity theories include Horava-Lifshitz gravity, F of R theories of gravity, F of G theories of gravity, while when we add new ingredient, it can lead to scalar tensor theories, scalar theories, vector theories, and the accumulation of these theories. While these modified gravity theories can lead to higher dimension gravity theories, which include some strings and branes inside it, and the generalize of the Einstein-Hilbert action, which can lead to Gauss-Bonnet theory and level up theories. So these are some modified gravity theories which can lead to which can explain the current nature of our cosmos, including some effects of the dark energy and dark matter on its dynamics. The simplest one is the F of R theory of gravity. Wisdal developed this theory in 1970 by just modifying the Einstein-Hilbert action. In the Einstein-Hilbert action, we have here, instead of the function of the Ricci scalar, we have Ricci scalar. While this is the matter action, which can vary from different values, which can have different values, and we can have as many scalar functions as as we want, but these scalar functions must correspond to the recent observations of our cosmos. Here kappa is the coupling constant, and square root minus g is basically indicating the square root of the determinant of the metric tensor. These are particular formalisms of the F of R theory of gravity, which include metric formalism, Platini formalism, and metric affine formalism. And these are basically such kind of formalism in which the metric tensor can be dealt independent, or the connection symbols can be dealt independent, or they can be used simultaneously. Further, Harquetel did some work in modified gravity theories, that is by generalizing or presented a theory by modifying the theory presented by Wisdal, and he modified the Einstein-Hilbert action by introducing a generic function of the Ricci scalar and the trace of energy momentum tensor. And in a similar way, we can generalize these theories, but the scalar function which we introduce in the action integral must have some compatibility with the observations. So F of RT gravity involves some couplings, and it has some Lagrangian formalism which corresponds to minimal and non-minimal. That is, it can have the dependence of the Ricci scalar with the energy momentum tensor. And it is basically a very good approach to study the current nature of our universe. It provides results for the conserved as well as non-conserved system. And it also permits to pursue some well-consistent cosmological models. So this theory also have some drawbacks, and these theories further need some motivation, or to do some work in this modified theories, one have to get some predictions with observations. Next, I will move towards the evolutionary phase, and the evolutionary phase is related with the stellar evolution, the cycle of a star from its birth to death and rebirth under the influence of its own gravity, as discussed by Dr. Izwana. So the stellar evolution includes formation of star. We have initially molecular cloud, and then we enter into the protostar and main sequence.
Dr. Zain, we are running out of time, so we have to end this meeting. So you can join again.
Okay. Thank you.
Okay. Thank you.
Hydrogen. And the temperature in these molecular clouds is 10 to 30 Kelvin and have high densities. Similarly, protostar is a warm clump of molecules referred as protostar. And this is basically a gathering of mass from its parent molecular cloud. And these last about 1,000 years. And several protostars can form into one cloud. What is main sequence star? It is the basically a cluster of stars where pressure from energy fusion balances gravity contraction, and central temperature increases to fuse hydrogen molecule, and it took around 40 to 50 million years to get here. The new star will spend the next 10 billion years as a main sequence star. Evolution. After millions of years, the hydrogen fuels that powers the nuclear reaction within stars will begin to run out, and they will enter the final phase of their lifetime. Over time, they will expand, cool, and change color. So the path they followed beyond that depends on the mass of the star. Star clusters. Star clusters are basically a couple of clusters which include galactic open clusters and global clusters. So we can see in this figure position of globular and open clusters that the open clusters are 4 kiloparsec away. And kiloparsec is basically the unit of measurement which is used in astronomy, which include 4,000 parsec, and one parsec is basically 3,260 light years. So this is the basically we can say that the open clusters are away from the initial stars from where it started around 4 kiloparsec, and then we can enter into the globular clusters which are 8 kiloparsec away from the initial star clusters. So open clusters include systems of about 10 square to 10 cube stars which found in the plane, spiral arms, and galactic nuclei, and it can have a diameter of around 1 to 5 parsec diameter. And they are rich in heavy elements, and ages range from 10 raised power 6 to 10 raised power 9 years. And this is the pictorial representation of the globular cluster, which is basically a collection of stars of around 10 raised power 5 to 10 raised power 7 and have very high density, and the diameter is 5 to 30 parsec. And 1 parsec is basically 3,260 light years. This is another pictorial representation of our cyclic formation of the stars. That is, initially we have the Big Bang, and about 13.7 billion years ago, the Big Bang happened, and now at the present state, we are living here. And about the range of 11.5 to 12.5 billion years ago, we have globular clusters in our galaxy formation. This is another pictorial representation. That is, initially we have stellar nebula, then we entered into every star, which ultimately upon evolution leads to red giants and enters into the planetary nebula, and upon evolution it will lead to the white dwarfs. And in a similar way, we can have for more massive cloud of dust, we can have the final fate as the black holes and neutron stars, which are basically we can say that these are the end stages of the evolution of our cosmic history. These are the physical features of the compact stars. That is, a star to be physically viable, it must have no singularity in the interior solutions as well as the surface of the objects. So we must have positive density, positive pressure, and radius must be positive. The density and pressure are maximum at the center of the objects and decrease monotonically while going out towards the surface. It must satisfy the null, weak, and strong energy conditions. And the first derivative of density, pressure, and string tension regarding radius should be 0 at the center, whereas the second derivative of the same should be negative. And the anisotropic factor should be 0 at the center. That is, we must have all kind of pressure to be equal. And the surface redshift must be positive and finite. So this is another pictorial representation how the universe is expanding under the influence of some dark constituents. The space between galaxies expand, not galaxies. That is, one galaxy is moving away from the other one, and the universe is expanding at an increasing rate. That is, we can say that our universe is expanding acceleratively. So this is some basic concepts related to the evolution of our cosmos. And regarding the structure scalars, we can have some basic ingredient in the theory of general relativity to be Riemann curvature tensor, and we can split mathematically using the 4-vector formulation the Riemann tensor into its constituent element. The first one is the electric part of the Riemann curvature tensor. The second one is the magnetic part of the Riemann curvature tensor. That is, every tensor can have, or we can say that when the waves propagate, it have both electric and magnetic constituents. So since the gravitational waves can be well described using the Riemann curvature tensor, so these fields must have some sort of electric and magnetic constituents, and these electric and magnetic constituents can be explained via some tensor. These are given here, like electric part of the Riemann curvature tensor and the magnetic part, and we can have some second dual of the Riemann curvature tensor, which is mathematically defined here. And these tensors can further be split down into its trace and trace-free parts. For spherically symmetric kind of geometry and with isotropic pressure, we can obtain some scalar functions associated with the electric part and magnetic part, as well as the dual of the Riemann curvature tensor. We can have another quantity related to some curvature components, the Weil tensor. However, the second dual of the Weil curvature tensor vanishes. So we can have only the second dual of the Riemann curvature tensor. And these tensors can split into their trace and trace-free parts. For spherical kind of geometries, we can say that these trace part of the second dual of the Riemann tensor can describe the energy density of the fluid, while the trace-free part controls the inhomogeneities in the energy densities. In a similar way, this trace part of the electric component of the Riemann tensor describes the mass density for the system in equilibrium or quasi-equilibrium, while the trace-free part shows the influence of local anisotropy of the pressure and density inhomogeneity on the Tolman mass. In a similar way, we can have only one scalar part associated with the magnetic part of the Riemann tensor, which yields all possible dissipative fluxes. But these dissipative fluxes for isotropic fluid vanishes, so we cannot have a magnetic part of the Riemann tensor in that case. If we have a plane structure, then we can obtain 5 scalar functions, while if we have cylindrical structure, then we must have to choose a particular form of the energy momentum tensor compatible with this cylindrical geometry. And for the compatible cylindrical fluid configuration, we have 8 scalar functions, which are named as structure scalars. While for the static axially symmetric space-time, we again have 8 structure scalars, but in that case, the magnetic part vanishes. While for non-static, we have 4 more scalar functions, which are basically the trace-free parts of the magnetic part of the Riemann curvature tensor. So these are the scalar functions which have their own physical significance as described earlier for spherical kind of geometries, and one can evaluate the further the significance of these scalar functions for the exact solutions of the modified or the Einstein field equations. Thank you very much.
Thank you so much, Dr. Zaim, for such a nice talk. So any questions from the audience? So I think there is no questions. So thank you once again, Dr. Zaim. Such an informative talk you have delivered.
Thank you very much, Dr. Sarish, for your kind invitation and organizing this wonderful program.
Thank you. So this ends today's session. Thank you so much for joining us today. And we are looking forward to seeing you in tomorrow's session. So, thank you. Allah Hafiz. Goodbye.
Thank you. Allah Hafiz.
Allah Hafiz.